Hello and welcome back. We have been discussing about second order optical nonlinearities, particularly second harmonic generation, and in the last class we derived a phenomenological expression for the second order polarization, and from there we said how we can get second harmonic generation. So, we also said that there is a necessity to synchronize the phase velocities of fundamental and second harmonic wave in order to have a decent amount of second harmonic output. So, we will talk about this what is the importance or in other words why this phase matching is so important in nonlinear optics. We will do that in a bit. Before that, we would like to talk about the process SHG. So, in the last class we when we derived that expression, phenomenological expression for second order polarization, we saw that there is a DC part and then there is a frequency dependent part, and this frequency corresponds to the frequency twice that of the fundamental frequency. So, now what actually happens there physically? Okay. So, when intense laser light acts on a matter, particularly if I take a nonlinear optical material, then under equilibrium condition you have a very symmetric charge distribution. So, this is random charge distribution everywhere. So, this is very much isotropic. Okay. Now, when a strong laser field acts on this one, so this is coming from this one, it creates a non-equilibrium state of this kind of charge distributed state. So, I can just show it by a cartoon where I can distort this charge distribution like this. So, this is random and equilibrium situation, and this is a non-equilibrium distorted condition of the charge distribution, and this is polarized, right. So, we create an asymmetry in the charge distribution, and when this is very much very large, then what will happen, this is a non-equilibrium state, it will not remain as it is forever. So, it will rather quickly would like to, okay, so this is the state when the photon is acting on this one, and this would like to go back to this state. When it goes back, then what will happen? It will release the energy in the form of light. Now, if I if I send in light of a frequency say omega 1, and if the distortion is not too much, that is the movement of the electrons from its equilibrium position is not too far, then I am going to have omega 1 back in terms of scattering, and this is a linear scattering, okay, or Rayleigh scattering that we are aware of very much. Now, if the distortion is really large, when the field is extremely large, then it can so happen that the energy that is coming back is much higher than my input. So, I can show that using an energy diagram. So, this is my ground state, and now if I just give a large amount of photons, the material is forced to take up that photon and it goes somewhere. We normally depict that by dashed line, we call it a virtual state, and because it will not stay in this non-equilibrium state for longer time, it will revert back to its isotropic condition, which is a stable equilibrium condition, and the result is the getting back the same frequency of light. This is linear scattering. Now, if my intensity is very high, what we can have, suppose I come with a frequency omega 1 prime such that omega 1 prime is equal to omega 1 by 2. Okay. Just for simplicity, okay, I could take like omega 2, omega 3, does not matter. Okay. Now, this is my omega 1 prime, and I will give you certain number. Suppose this one was say 532 nanometer light, good choice, it is a green color, so 532 nanometer light, and I get back my 532 nanometer light in terms of linear scattering or Rayleigh scattering. Now, if I have another wavelength which is having half of the frequency, that means twice that of the wavelength. So, essentially omega 1 prime is 1064 nanometer. Okay. That is very easy to calculate if you know the conversion of frequency and wavelength. So, now what I am going to do, I am going to allow the material to interact with 1064 nanometer light, that is my omega 1 prime, and having very large electric field, okay, coming from a strong laser beam. So, if I write somewhere here, so this guy will take it here, this is my 1064 nanometer, right. Now, the electric field is very strong, so while one photon takes this molecule up here, but there is possibly no real state, there are too many photons there which are ready to interact with the material even at that condition. Because of the large density of photon, that can force the system from here to take up a photon further of 1064 nanometer and go up here. Okay. So, once it goes here, it has reached such a condition. So, again it would like to come back to this condition, which refers to the ground state. So, from here it will come back to the ground state directly here. Now, this corresponds to this amount of energy, which refers to 532 nanometer. So, I have used two 1064 nanometer light from in an intense laser light and force the molecule to take two of these photons to go to some polarized state and then scatter back the total energy that it consumed, which is 2 photons of 1064 nanometer essentially, which is equal to 532 nanometer. So, this particular process that I just showed you is known as second harmonic generation. Okay. Now, I could, and it is done, that if I have sufficient photon density from a high intensity laser, it may not stop here. Okay. In some cases, it can take another one photon here and it can come back. So, there it will come back with a photon which is higher than even 532 nanometer. Okay. So, this energy, if it comes from this place, this will correspond to 355 nanometer approximately, and this is known as third harmonic generation. you can imagine if it would have taken 4 photons successively and jump back to this ground state, it would emit a a photon whose frequency would be 4 omega 1 prime, and that would equate to 266 nanometer, and that is known as 4th harmonic for this particular 1064 nanometer fundamental line. Okay. So, this is the pictorial representation of this second harmonic generation or third harmonic generation or fourth harmonic generation and so on. So, in general this is the picture for harmonic generation process. So, this is a specific process in second order among the second order nonlinear optical processes. Now, if I have a situation where I come up with 2 photons, 2 incident photons having 2 different frequencies, what we may have? We may have the following situation. So far we have shown like all the photons are of equal frequency. Now, if I have say one photon of 532 nanometer and then another photon of 1064 nanometer, the lengths are not to be scaled. Okay. So, I still have my laser source, so I can force my material to take up the photons. So, if it takes one 532 nanometer photon and then another 1064 nanometer photon from there, so it will go up here and then it will release a photon of the energy which is equal to the sum of both of these photons, right. So, because the energy must be conserved, right. So, energy conservation must hold. Okay. So, I can say that if suppose this is my omega 1, this is my omega 2, okay, do not confuse with this terminology anymore. If this is my omega 1 and this is omega 2 and this one is something omega 3, then my omega 3 must be equal to omega 1 plus omega 2, because I must have the energy conservation for this particular process. So, at this point if I ask you, I have used 2 photons having frequencies 532 nanometer and 1064 nanometer, they have some way mixed in the material and generated a third photon having omega 3 frequency. So, corresponding wavelength. So, this is I should correct this one, this is actually lambda 1 and lambda 2. Okay, I can have the corresponding omega 2 and omega 1 of course, and this have lambda 3. So, I have this lambda 1 equals to 532, lambda 2 equals to 1064. What is my lambda 3? Okay. So, my question is lambda 3 is what? How do I find that? That is very easy to do, because I know this equation from energy conservation. So, this is my unknown. So, how to do that? It is 1 by lambda 3 equals to 1 by lambda 1 plus 1 by lambda 2. Lambda 1 and lambda 2 my incident photons, lambda 3 is the photon that I am getting out of this nonlinear process, okay, which is again a second order nonlinear optical process, okay, because I am using 2 different photons to get a third single photon. Okay. So, now you can immediately check this. I am talking about 2 different frequencies. If my lambda 1 and lambda 2, so if lambda 1 equals to lambda 2 equals to say some lambda, Then what will be the process? Then this process will lead to 1 by lambda into 2, right. So, essentially my lambda 3 is equal to lambda by 2. So, lambda by 2 means essentially twice the frequency. So, that means that is a second harmonic process. So, this will give me second harmonic generation when lambda 1 equals to lambda 2. When lambda 1 and lambda 2 are different, this particular process is known as some frequency generation. So, in general, if lambda 1 is not equal to lambda 2, this one will give me some frequency generation. Okay. And in this way, you can calculate what is the frequency of this particular photon, that is what is lambda 3. So, lambda 3 will be equal to 1 by 1064 plus 1 by 532, right. So, essentially that will be 3 by 1064 nanometer, right. That is 1 by lambda 3 equal to. Therefore, lambda 3 is equal to 1064 by 3 equals to roughly equals to 355 nanometer. Okay. And this process is also known as wave mixing. Why? Because you are having total 3 different photons here. Okay, we are taking the second order process only. So, 3 different frequencies, they are as if being mixed. So, I can show it pictorially that this is suppose a nonlinear optical crystal, and one light is coming here, another light is coming here, and the third light is coming out. So, they are being mixed here, and this is why this is also known as wave mixing. Wave mixing has tremendous importance in various different fields, okay, starting from physics, chemistry, spectroscopy, material science, and in electrical engineering. Everywhere you will find the applications of this process of wave mixing, which is a nonlinear optical phenomena. All right. So, let us now start our discussion on phase matching. So, we said that we need a synchronization of the phase velocities So, we said that we need the synchronization of the phase velocities corresponding to the fundamental and the harmonic wave. Okay. Now, what is phase velocity? So, phase matching is essentially the synchronization of So, we have to match their phase velocities. Phase velocity is the velocity of a light wave, which is essentially a plane wave when it propagates through a medium, correct. And how and this medium generally we characterize, so characterized by the refractive index. Okay. So, if I take an NLO medium through which the wave is propagating and we are considering a velocity as phase velocity. So, this nonlinear medium is characterized by refractive index Ri equals to n. Okay. And this refractive index in general is frequency dependent. Okay. And how is this phase velocity related to this refractive index? So, the thing that we know is this, where omega is the frequency and k is the wave vector of the light that we are considering, of a plane wave, and this we can write in terms of the velocity of light and the refractive index n omega. Okay. Now, at this point the important question to ask is why phase matching is so important. We have been asking, okay, we need to have phase velocity, phase matching. Okay, so why is it so important to get this phase matching? So, at this point we will consider a fundamental wave having a frequency omega 1 and a wave vector k1. So, to answer that, let us consider fundamental wave. So, many cases in books you will also see this is called a polarizing wave. Okay. So, they are same. So, the particular frequency that is used to induce nonlinear polarization is known as polarizing wave or fundamental wave. Okay. And this fundamental wave is characterized by frequency omega 1 and wave vector k1. What it will do? This fundamental wave will induce polarization at the second harmonic frequency, which is equal to 2 omega 1, right. So, this will lead to polarization created at frequency 2 omega 1 and corresponding phase velocity will be 2 k1, right. Now, the SHG that will be created, that will be characterized by its frequency omega 2 and wave vector k2. So, for SHG process it has to be that omega 2 equals to 2 omega 1, it is bound to happen, and this wave vector k2, it may not be equal to this 2 k1. Okay. So, generally actually it is not equal to 2 k1, this is in general. Okay. So, now if that is true, then how do I achieve the phase matching? Okay. So, the phase matching will take place what do we need is, I can write as k2, which is function of frequency 2 omega 1 is a sum of k1 omega 1 and another photon having the same value, right. So, this is what is needed to be fulfilled if I really want to have a phase matching if I want to have the SHG to occur. And if I write it in general term, in general term, this I can write K3 omega 3 equals to K1 omega 1 plus K2 omega 2, when I am not certain if it is omega 1 equals to omega 2. Okay. So, this is most general form, and I can rewrite this one in terms of delta k, which is equal to K3 omega 3 minus these two quantities, that is K1 omega 1 minus K2 omega 2, and this delta k must be 0. Okay. So, this is the condition to achieve phase matching in a nonlinear optical medium, okay, upon interacting with the intense laser light. Okay. Now, interestingly, this wave vector is related to the momentum, right, because k is related to the momentum p, which is k h cut, correct. So, p is equals to k h cut. So, this relation simply tells me that the energy exchange here, it essentially what I am having is an energy exchange between different photons, right, coming from fundamental omega 1 to the second harmonic 2 omega 1, there is an energy exchange. So, this energy exchange is between these waves are possible only when I have this equation fulfilled, okay, or in other words, my law of conservation of momentum is intact. Okay. So, law of conservation of momentum holds. Okay. So, if I consider this process of wave mixing happening in a collinear geometry, that is my wavelength 1 is coming in the same direction, this one is also happening in this one, and the outgoing light is going in this direction. So, in that case, what we can write in terms of the refractive index and the frequency following this general relation, and we know how this omega k and the refractive index is related. So, knowing that, I can write omega 3 equals to n1 omega 1 plus n2 omega 2, right. So, now for SHG, I have to have omega 1 equals to omega 2, and not only that, I should also have omega 3 equals to 2 omega 1 then. So, if I put that, it is n3 into 2 omega 1 equals to n1 omega 1 plus n1 omega n2 omega 1, right. So, so n2 also here will be n1 because I am considering the same frequency. So, for same frequency it will face the same refractive index. So, essentially it will be 2 n1 omega 1. Now, this is true only when the I can write in terms of this one, this is the so N3 is a to start with, N3 is a function of omega 3, omega 1 is a function of so N1 is a function of omega 1, N2 is the function of omega 2. So this is only possible when I have this condition fulfilled, and this this holds only if N2, a function of 2 omega 1 is equal to N omega 1, is known as index matching condition and also known as wave vector matching condition. Okay. Now, in general, this condition is not fulfilled because I have two different frequencies, and that due to dispersion these two frequencies will have different refractive indices. So there are certain ways to fulfill that. We will look at that in the following class. Thank you very much.